Our next lesson in our atomic structure and nuclear decay unit is on periodic trends. Looking at our learning standards and targets here, this is the final learning target for our periodic table standards. We want to be able to identify and apply trends in reactivity, electronegativity, and atomic radius. So all of these examples that we're looking at today are known as periodic trends. A periodic trend is simply any property of an element that has distinct patterns based on an element's position on the periodic table. The three that we will look at today, you can see there above in the learning target: reactivity, electronegativity, and atomic radius. We'll define each of those here. The atomic radius is probably what you think of it, just the size of the atom. It's how big the atom is from the nucleus to the outermost valence electron. Electronegativity is the attraction for electrons in a chemical bond. And reactivity is the ability of an atom to form bonds. So jumping right in here, let's take a look at the periodic trend of atomic radius. Here is a very useful image of us that really just shows us what our trend is in atomic radius. Notice, as if we work from right to left across the periodic table, across any period, the atoms get bigger as we work from right to left. Or, as actually we commonly talk about it, going from left to right, the atoms get smaller. As we go from top to bottom, that atomic radius increases. The atoms get bigger. So as we can see here, atomic radii, they decrease moving left to right across the table, and they increase moving top to bottom down the table. Now the more important question here is why. We want to understand why the size of the atoms have a trend that fits this description. Well, let's consider going left to right here. As we move left to right across the table, so if you just look at your periodic table, for example, look at period number 2, where we have lithium here, and then beryllium, then jumping over here, boron, carbon, nitrogen, etc. As we go left to right, remember, we're going to add an additional electron to the atom. Now you might think, if I add an additional electron, shouldn't that make the atom bigger? Because I have an additional electron, it's in that same energy level that's already there, that valence level. Shouldn't that increase the repulsion, spread the electrons out a little bit, and make the atom bigger? Well, if that was the only thing that was changing, you would be right. The thing is, though, is we're also adding an additional proton to the nucleus. As we go from lithium to beryllium, we go from 3 protons to 4. From beryllium to boron, we go from 4 to 5 protons. Because there's an additional proton in the nucleus, this is going to increase the amount of charge in the nucleus. There's going to be more positive charge there, which means it will increase the attraction between the nucleus and those outer level electrons, or the valence electrons, and it pulls them in closer to the nucleus, so it makes the atom smaller. So this explains why it is, as we go from left to right, why this atomic radius decreases. Because of that additional nuclear charge, that charge pulls the electrons in tighter, makes the atom smaller. So what about going down? Well, if we go down the table, moving down adds lots of protons to the nucleus. This should make the atom smaller, right? Based on what we just said, more protons, additional nuclear charge should pull those electrons in even tighter. But you have to think about what else is changing. We're also adding lots of electrons. So for example, if we talk about going from lithium down to sodium, we go from 3 protons to 11 protons. You think, geez, that's way more positive charge in the nucleus, should pull it in tighter. But remember, we add a lot of electrons, at least one of which goes into an additional energy level. Because lithium would only have 2 energy levels because it's in period 2, whereas sodium would have 3. If I go down another group here, another period, potassium would have 4. So that additional energy level moves those valence electrons farther from the nucleus. So that additional energy level, because it moves them farther from the nucleus, it makes the atoms bigger despite that increased nuclear charge. In other words, what we're saying is that increase in number of energy levels has a bigger effect than adding the number of protons that we do to the nucleus to increase the nuclear charge. So the atoms get bigger as we go down the table. So what we want to do then is, knowing these trends of what happens to the radius, we want to be able to look at a series of elements and order them. In this case, our question tells us to order each atom by increasing atomic radius, so smallest to largest. So we're given these particular elements here: arsenic, gallium, bromine, potassium, calcium. So find those on your periodic table. And you'll notice these all happen to be in the same period. Okay, these are all in the fourth period of your periodic table. So find all of those, and based on the trend, we know that as we work from left to right, the atoms get smaller. So if we want to go from smallest to largest, as we were asked to do here, we want to work from right to left across this period. So the farthest element to the right there, and those elements were given as bromine. So bromine would be the smallest. And then moving to the left, the next element I'd run into is arsenic, followed by gallium, followed by calcium, followed by potassium. Here's a similar question. Order each atom by decreasing atomic radius. So I want to go from largest to smallest. And take a look at the elements we're given here: silicon, lead, germanium, carbon, tin. All of these elements happen to be in the same group. Okay, so this again makes it somewhat easy for us. So if I'm going largest to smallest, I would want to start at the bottom, because recall atomic size increases as we go down the table. So the element in that grouping there, that's at the bottom of the table, would be lead. Okay, and then working up, I would have tin, germanium, silicon, and carbon. Okay, one more example here, and you'll notice all these elements we're given are neither all in the same period nor in the same group. So this does make this a little more difficult. But if we just think about the trend, I know as I go from left to right, my atoms get smaller. As I go top to bottom, they get bigger. If I want to order these from smallest to largest, then I want to look at this list of elements here. I want to find the element farthest to the top and to the right of the periodic table, and then work my way down and left, because then the atoms get bigger as I work down and to the left. So the smallest in that group would be chlorine. That's farthest to the top and the right. And then if I look at my next element going left and down, I would get to sulfur, followed by arsenic, followed by indium, and then barium, cesium, and francium. So you'll notice these are just ordering the elements from the top right of the table to the bottom left, because that would be by increasing atomic radius. Alright, our next trend is electronegativity. Recall that electronegativity from the initial slide is the attraction that atoms have for electrons in a bond. And actually, your periodic tables have electronegativities on them. They're listed there. Some periodic tables have them on there, as yours do. And you'll notice, looking at that, or at this picture that just popped up here, that fluorine has the largest electronegativity at 4 in the top right-hand corner. Francium is the lowest at 0.7. So in other words, electronegativity, it increases going left to right. It would also increase going bottom to top. Typically we talk about going top to bottom. So top to bottom, it would decrease. So the electronegativity, it increases moving left to right across the table, and it decreases moving top to bottom down the table. And again, the important question here is why. We don't just want to know what the trend is, we want to understand why the trend is what it is. So if I think about moving left to right across the table, remember that decreases the atomic radius. The atoms get smaller as we work from left to right across the table. Well, that means there's going to be an increased attraction between the nucleus and valence electrons. And remember, electronegativity is the attraction for electrons in a bond. Well, the electrons that do bonding are valence electrons. So in a way, you could kind of say electronegativity is the attraction atoms have for valence electrons. Well, because these atoms are smaller, there's an increased attraction between the nucleus and those valence electrons as we work from left to right. Also, the farther to the right we go on the periodic table, so if we work to the right across any period, again talking about the second period, lithium to beryllium to boron to carbon to nitrogen, etc., those atoms want to gain electrons more because they're closer to their octet. The farther to the right we go on the table, the closer they get to that full octet, they really want to gain electrons. And so this increases their electronegativity. Now, one thing to note here is that we do not include noble gases in this discussion, because noble gases are kind of their own breed. We call noble gases a group 18 out here and to the very right. They already have a full octet. In fact, they don't really fall into that atomic radius trend that we saw on the previous couple of slides. So when we talk about moving left to right, the electronegativity increases. That is absolutely true, but we wouldn't include the noble gases, group 18, in that. So what about moving top to bottom there? Okay, why does the electronegativity go down? Well, do recall that as we go down the table, that our atomic radius, the size of the atoms, gets larger. And so using the same reasoning that we did before, we know that this should decrease the attraction between the nucleus and valence electrons. And also, as we go down the table, those atoms want to gain electrons even less. Even over here on the right side, where if we're talking about group 17, if I go down fluorine, chlorine, bromine, iodine, etc. Over here talking about group 17, I get down towards the bottom of group 17, for example, iodine, it does not want to gain electrons as much as fluorine. Okay, most of that's because of its atomic radius, because it's bigger. There's less of an attraction there for those electrons, so it's not pulling on them quite as hard, and so the electronegativity is less as we go down the table. So again, like with atomic radius, we want to be able to order elements by their reactivity or in this case electronegativity. So here I ask you to order each atom by increasing electronegativity, so smallest to largest. And I do happen to just use the same elements I did on the previous questions, so we kind of already know where they are. So smallest to largest, all these elements here are in the same period. So working left to right. So if I want to go smallest to largest, I do want to go from left to right across the period. So that would be potassium farthest to the left, followed by calcium, gallium, arsenic, and bromine. Okay, now I want to order each atom by decreasing electronegativity, so largest to smallest. And all of these elements are in the same group, so going up and down the table. So if I want to go from largest to smallest, I'll start at the top and work my way down. So that would be calcium, followed by silicon, followed by germanium, and then tin, and finally lead. And then lastly, we have a combination of elements that are not all in the same group or period. So thinking about my electronegativity trend, the largest electronegativities are in the top right-hand corner of the table. So looking at this order here, guys, our increasing atomic radius would start in the bottom left-hand corner. And we'd go from chlorine to sulfur to arsenic to indium to barium to cesium to francium excuse me, this is electronegativity. I forgot to change the name here. So this is for electronegativity. So we'd start with francium and then work our way up through chlorine there, going bottom left to top right. Alright, our last trend here is reactivity. And what we have to consider with reactivity is that, do remember, it is the ability of an atom to form bonds. And we have to consider metals and nonmetals separately because they react in opposite ways. Recall that metals react by losing electrons and nonmetals react by gaining electrons. So talking about nonmetals, we want atoms with a greater attraction for electrons. They're going to be more reactive. So what that means is we want small atoms with large electronegativities. Large electronegativities because they have a greater attraction for those electrons. Small atoms because it's closer to the nucleus. For metals, it would be the exact opposite. We want metals want to lose electrons when they react. So we want atoms with a smaller attraction for valence electrons. And this would be large atoms with small electronegativity. So I'm looking at the picture here. For metals, the greatest reactivities are down here at the bottom left, so it increases going towards the bottom left. For nonmetals, it's the top right. And notice here we're ignoring the noble gases, group 18, because they don't really react with anything. So thinking about this order here, if we order elements by increasing reactivity, here we have some nonmetals, sulfur, phosphorus, arsenic, oxygen. From least to greatest, the least reactive would be the nonmetal towards the bottom left, so that would be arsenic, followed by phosphorus, and then sulfur, and then oxygen. Likewise, we want to order these metals by decreasing reactivity. So decreasing reactivity, we'd start with the greatest in, so that would be the bottom left. So going francium, rubidium, strontium, and aluminum.